So one kind of exponential function that's really important to us is one that comes with something called the natural base e. That letter E comes from the name of the mathematician whom it was named after, and that was Leonard Euler. Leonard Euler was one of those brilliant mathematicians for whom a lot of things was named after, but in this case the letter E is memorialized for him, and it's about 2.718288182. Actually, it's not a repeating decimal, that's rounded up. I went through and I found my e to the x by doing this one here. If I put in 1 and e to the x right there, whoops, let's try that again, 1, and then I put in my e to the x, here it is. Spelled out in great detail. You can see that this is a huge, huge number with lots and lots of decimals that continue to not repeat after a long time. In any case, this particular function, which is kind of cool, is based on this natural number. How does this natural number come about? Well, if you were to actually go through, and you can fiddle with your own calculator if you care to, your calculator, by the way, if you're interested in using these particular kinds of functions, e to the x on your calculator is found right here. Circle this in a color. Right here on this button. If you go to the NAP's physics department and check out Foundation, they have a calculator guide there that will help you with this one. In any case, if we were to go check this one out, we just start putting in numbers for x and let x get really, really big, what do you think would happen? Well, it turns out that this particular limit is in fact 2.71828182818281828, depending on how large you cared to make x. So this is a really important function. It turns out that this particular function comes up in all kinds of natural processes that we could show, and we will later on at some point in this chapter, for functions such as population growth, radioactive decay, even bank accounts. So this turns out to be a really, really important function to us, and we would want to know what we can do with it. Well, I'll show you one thing that we can do with it. We can graph. Here, for example, is the function f of x equals e to the x. And how do we know what points are on it? Well, easily enough, we can map these points by looking at the values. Certainly, e to the 0 would equal 1. So this is the kind of graph that would pass to the point 0, 1. We could say that x equals 1, y equals e, which seems kind of like a funny thing to graph right here. But e, well, if we're graphing, notice that e is about 2.7 right here along your y-axis, 2.718 or 72 or so along your y-axis. So it's between 2 and 3. Likewise, if we were to put in negative 1, we would get negative 1 over e. Again, 1 over e, since e is between 2 and 3, closer to 3 than it is to 2, it turns out that e will be between 1/3 and 1/2, right? Because those inverses change the position of our bases here, right? So 1/3 less than e, 1 over e less than 1/2. So somewhere in there is our 1 over e number. Well, okay, all of those things said, how does that help us? Well, we still have a horizontal asymptote to the left at y equals 0. And as x goes towards positive infinity, y goes towards positive infinity. In other words, it acts like every other exponential function in the universe would act. So let's take a look at a modified function right here. Let's try f of x equals 1/2 e to the negative x. What shifts or translations are happening right here? Well, first of all, we've got that negative x business. And if you recall that from a couple of videos ago, negative x meant that we're going to have our horizontal asymptote at y equals 0 off to the right. The other thing that we're going to notice right here is that this 1/2 is going to be a vertical stretch or shrink of the graph at left right over here, this e to the x graph, by a factor of 1/2. So let's think about what that will mean. In the original graph, our function f of x passes to the point 0, 1. Well, it's no longer going to pass through 0, 1, right? Because we're multiplying by 1/2. So it will pass to the point 0, 1/2. Right? Again, just so that you see it, if I said f of 0, you would realize we're taking 1/2 times e to the negative 0. Well, it's just 0. That's 1/2, right? Okay, so that makes it a little bit easier to deal with. If we were to put in 1, right, normally we would get 1 over e, right? But this time we're taking 1/2 times 1 over e. So at x equals 1, we're going to get the point, and we can express this as an exact value, as we should. 1, we're going to get 1 over 2 times e. Now again, that's somewhere between, if we think 1/2 e, right, 1 over 2e will be somewhere between 1/2 times 1/2 and 1/2 times 1/3. So somewhere between a sixth and a fourth. On the other side right here, if we put in negative 1, that means that we're going to have e to the positive first times 1/2. Well, let's see, 2.7, about half of that is going to be about 1.54 or so, right down here. And if we think about that one, right, we could actually say, well, that means that at negative 1, we're going to get 1/2 of e to the positive 1, so that's e over 2 as our exact value. So on this graph, our function decreases from negative infinity, passes through our 3 points at negative 1 e over 2, 0, 1/2, 1, 1 over 2e, and then it decreases towards 0, so that's where our horizontal asymptote is to the right this time. And that would be our graph based on our exponential natural base function.